Uh, all the participant except the speaker, their mic will be muted. So you just listen the session, and in question answer session, raise your hand. There is an option in the taskbar where you can click and your hands will be raised. And I will unmute you. You can ask the question from the expert. Okay. After the session, you will also get the quiz, which you have to do it in one day and submit. Okay. So let's start. Welcome, Mr. Asit Verma.
Thank you. Thanks very much for having me here.
Welcome, sir.
So should I go ahead and share my screen?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you. So let me know once my screen is up and you guys are able to see.
Yes, we can see it.
Okay, so I think, yeah, thanks for introducing me. And as suggested, so I'm working as a tech lead in Intel client organization, so which basically uh, productizes the client. Uh,
Suraj Kumar. Yes, he's muted.
okay, so yeah, so basically my group productizes the client roadmap, and I think most of you, or at least some of you, must have used Intel microprocessors. And if you are having some of the laptops and you are using Intel microprocessors, you must be aware about like Core i3, i5, i7. So currently we are in 10th generation of core products, and the power and performance, battery life, responsiveness of these products, these are some of the things which my team works on. So we basically drive across the organization for delivering the best in class power and performance on all these platforms. So that's what we do, and I will go into slightly more details, although assuming that the students here are from class 12 and first year and second year, maybe I have just tried to make it more generic. And if you have some questions, just keep it with you, and at the end we can discuss some of them if time permits. Okay, so let me quickly go through the so let me quickly cover what exactly the platform concept is, and what does this PNP, that basically power and performance engineering, is about. Okay, so when we define a platform, it's basically is a combination of various software and hardware components. Sometimes we also call these components as ingredients, and basically this combination of various software and hardware uh, is combined in such a way to do a particular task. So for example, we can take browsing. So when you are browsing on your computer, there are various ingredients which needs to work together, right? For example, when you are browsing, you need to have the internet connection, maybe via Wi-Fi or maybe via modem, right? And then you need to have the browser, for example, whether it's a Chrome, Edge, or for I mean Mozilla. Then you need to have the operating system. Then for audio, you need to have some audio subsystems. Now if you are like, let's suppose if you are doing video conferencing, you need to have the camera. So basically what I'm trying to say, that the platform delivers a particular task, and that's why it requires to have various components working in the optimal way, and that can be various hardwares and various software components of various firmware components. So that's the platform engineering we do. Now, when we talk about the platform power and performance engineering, that's again a more specialized area of the platform engineering. Okay, and how we can define platform power and performance is as a part of platform product R&D and execution to ensure best in class battery life, performance, and user experience for use cases, and is within product timeline. So when we do all these optimizations and all, basically we need to ensure that we are delivering within a given timeline. So you might be seeing that, okay, there is a ninth gen of core products already in the market, or 10th generation is already in the market, or 11th generation is going to be getting productized this year. So there is a fixed timeline where we need to deliver all these products, and that's why all these optimizations and all we need to do in a timely fashion. It's not like that, okay, we keep doing these R&Ds, but it needs to be delivered within the product timeline. So I hope that this basically tells you what exactly the concept of platform engineering. And then when we say power and performance, what does that mean? I think the next slides or next topics will we will have discussions more on into that, and you will have more clarity on these concepts. Okay. So I think I will just briefly touch upon the agenda, and then I will go one by one. So I think we already saw the definition of what's the platform engineering and the power and performance engineering is about. And I think we also came across the words like use cases, that we do the some of the PNP optimizations for a in a given timeline for a specific use cases, right? Now the next agenda item or the topic, we will discuss more about what kind of these use cases are. And I assume that you guys are the best to tell that what you do with the laptops, because like you are the real users, so you must be knowing more about from more than us, that what exactly you do. But I think some of them I have tried to list it here, and we'll go about that. Then I'm trying to explain a slightly more detail on the platform side. I already briefly touched upon by giving an example from browsing, but then we'll maybe we can just touch more into detail that what will be the different basic components and all of a platform, right? And then as our topic is also about power and performance optimizations, I will try to explain a simplified power equation, and based on that equation some techniques that can be used to optimize power or improve performance. So we'll go into slightly more detail once we go to the topic number 4. Then we will briefly touch upon once we talk about a use case and its power consumption. So what is the distribution of this power into different components? So for example, if it's a 100 milliwatt being consumed for a specific use case, let's say browsing, so how much the different components of the platform will be consuming out of that. So we'll just take one example again, that can be different for different use cases, but we'll briefly touch or go into slightly detail on one of the use cases, which is a static content on the display. Okay, anyhow, we'll once we go into that topic, we'll go into more details. Then the sixth topic basically will try to calculate some battery life for some of these use cases. We'll take some already available examples in the market, and then I will explain that how we can do these battery life calculations. Also, there are certain or different specifications available for these battery lives available in the market. So we'll touch upon on both. We'll definitely have like few exercises also at the end, just that you guys have some more clarity on that. Okay, and then I think we'll open for the discussions. Okay, so I think you can also brainstorm on this topic, which is basically what we do with personal computers. I have just tried to list few of them, but I'm sure that you may have more things in your mind. So the first type of workload or the use cases, the category I have used is browsing, because this is something which we do nowadays heavily, and some of the telemetry data taken by some of the big giants like Microsoft, Google, and all, we have found that almost 60% of the time people are either doing browsing or browsing related applications or clouds. So now this browsing activity is one of the predominant use cases for most of the segment. However, like I'm this is for the general users, but you can also have some of the segments which are particular for specific you can say a segment. For example, there could be few guys who could be hardcore gamers, so they may be doing 90% of the time gaming on their laptops. Or there could be uh, someone who is doing some creative work. For example, they may be doing some video editing or photo editing for some of their professional work. So maybe they might be doing 90% of the work in the creativity. So but I think in general, for most of the users like us, like almost 60%, we are doing browsing nowadays. Now, in the browsing also, we can again divide into the different subgroups or sub use cases. I think we are pretty much using nowadays for different social networking sites like Facebook, Instagram, Twitter, or Telegram, or many more, right? Then we also use for emails, online shoppings, online games. And nowadays actually, I mean, like we know that the applications also slowly are moving to the clouds. So now I think that we are also some of these applications are through browsers actually, by the way. So so some of the apps we are accessing through browser, although I have not mentioned here, but that's one of the area which is developing pretty fast. The other category which I have written here is media workload. Now, in this case, I mean, some of the users definitely do. So, for example, video playback. So you might have some video on your local disk and you can keep playing it. Although now this is slowly becoming less relevant, and the more relevant media workloads now are streaming through YouTube or Netflix or some of the other applications like Hotstar or something like that, right? Playing the video from the local disk is I mean, like now very few people do that. Okay, the third category which you can see is playing games. As I said, that there could be some hardcore gamers, but even if someone is not hardcore gamers, they can spend some time in gaming, like earlier, like some of the popular ones were Angry Birds, Asphalt, and others. I think I'm not a heavy game user, so I don't know which all are the new trends in the games right now. But I'm pretty sure that there are few guys who always are engaged into gaming and all, especially the 3D games I'm talking about here. By the way, there are 2D games also, but this is there. There is also, as I said, that the online games, those are also the new trends which are coming. So those are some of the new use cases which are becoming quite popular nowadays. The fourth category, I mean, if you see here, something we call it as productivity. And we call it as productivity for the tasks like when we use Microsoft Word, or we do some typing, or we just read some PDF, or create some PDF, or when we create some PowerPoints or files, when we do some analysis through Excel, or some statistical analysis through Excel. Similarly, we take some notes. We also write some codes through some of the editors like Eclipse. So these are some of the works which we call it as productivity, because it has some outcome, right? And and by the way, I think there is also now some of these productivity apps are going on the cloud, as if now most of them are locally available, I mean locally available on the disk. But for example, Microsoft 365 apps are a cloud based application, so these are slowly also getting migrated to cloud. And I have not separately written down the cloud as a separate segment, but yeah, I think going forward, that is becoming a trend, and that is getting more popular day by day. I already mentioned the creativity category, where we do some kind of photo, video editing, painting, so some kind of creations where we do. The other kind of categories which is very popular nowadays, and especially in the lockdown, we can find out that okay, these are some of the apps which has really become so popular, and it has given us interface or platform to have connection with multiple people and have something like Zoom, which we are right now also using, then Skype or Google Meet. So these are some of the popular apps in the video conferencing side. And I have just given some example, but there are many other apps which are there. So I think these are some of the category of the workloads or use cases which we predominantly do in the personal computers today. Now these things are always evolving, and we need to keep gathering the data through telemetry that what people are doing, so that we can understand what user is doing from these computers, and so that we can evaluate that, and we can also optimize both power, performance, and use cases. For example, I will give you something like how these workloads could be different in terms of the demand or the requirements. So for example, if you see browsing, so in browsing, what we do, so in general, when we are doing browsing, basically some pages will get loaded, then again we click on some link, then again new pages come. So in browsing, what happens usually, you will have some browsing pages getting loaded, then you stay at that place at that page for some time. So from user perspective, what happens when the page is getting loaded, right? The user responsiveness needs to be fast, or you should not perceive that okay, there is a lagging while you are loading some page. So that becomes a performance category, that you need to perform, or you need to have a better user experience while you are loading a page. But once you have loaded your page and then your content is basically not changing, then ideally you should go into the low power mode and save some power. So browsing becomes one of the bursty workload, where whenever there is a requirement to load a new page, you should be able to burst so that you can perform at the desired or higher performance. You can basically load that page faster than what you can, and then again you go to the low power modes to save power, right? Now let's talk about some of the media workload. So when you are playing a video playback, what happens, like frame by frame you keep basically decoding and putting it on the display. So this becomes a kind of consistent workload where the demand and all will be quite consistent. So it's not a bursty workload. So what you want is to run at a frequency which is optimal, not too high, because if it's running at a too high, it will burn more power. By the way, I think we'll go into the power equation to understand why running at the higher frequency you burn more power, and running at the lower frequency you burn less power. So but I was just talking about that, okay, maybe a media kind of workload where the demands are not busty, you want to operate at the least frequency mode, where the throughput is sufficient enough to give you the good user responsiveness or user experience, but you don't go for a higher frequencies and all, because your I mean like the power consumption will be higher, right? And such as, let's take about the productivity, right? So when we talk about the productivity, what you do, like for example, you are launching Word, or you are launching PDF, or you are launching PPT or Excel. So there is a launch of these applications. So whenever you are launching, again, you require user responsiveness or fast responsiveness. And then again, you do something. For example, OneNote, you launch the OneNote, but then you are writing something on that, so it goes into the idle mode. So it's pretty much similar to browsing, where while during the app launch you want a faster response, but once the app is launched, basically you need to go into the idle mode, or you need to be responsive only when you are doing something, typing or something else, right? So that becomes another category, that again this will be bursty in nature, that you should just burst to a higher frequency, operate maximum, and then go for the idleness so that you can save power, right? So I mean, yeah, so I just wanted to give you the why these use cases analysis is important to understand, because once you know that okay what is required, then only you can go and optimize either power or performance or user responsiveness for that segment. And to know what users are doing with the laptop or PC is very important for us. And what the new trend is coming, for example, the new trend, some of the new trend is like AI related workloads, right? So many of the companies are now moving into the artificial intelligence or machine learning. So we need to just see that okay, once they do that kind of operations, which kind of instructions will be required, or if we can come up with some kind of new instruction set which can give you a better performance for that category of work. So for example, Intel has come up with OpenVINO for such kind of or VNI instruction, we call it as, for this new category for AI related work. So yes, it's important for us to understand what the user is doing. Okay, so let's go back and see where we are. So I hope that we understand what are the different use cases and why it's important. And let me go to now the basic block diagram of a platform, and then we'll try to understand why it's important to know that which all components are there. Okay, so I hope that this page got refreshed. So this is one of the you can say the platform block diagram for Intel 7th gen core processor. It was namely, code name was KB Lake, and it got released in 2016, I assume 2016, 17, yeah, I think 2016, yeah. Okay, so I just want to touch upon the different components which are there as part of the platform, and let me take it from this side. So you can see system memory, right? And I think now for us it's important to understand what all the different components which make a you can say a computer platform or your personal computer, right? So I think I don't know, maybe in first year or second year, if the microprocessor has not started, and I assume that okay, maybe till class 12th also there is no subject on the microprocessor, but most of you are already using smartphones or some kind of devices, so you know what is that. And then many of you guys are from the computer background, so you know what is microprocessor, right? So now in modern days microprocessor, it needs to support the various activities, as we have seen that various kind of use cases are there, and that requires different kinds of support of hardware and software. Now one of the important components which you guys already know is the CPU, right? Central processing unit, which does all kind of arithmetic logical operations. uh, but along with that, for the microprocessor to work, you know that there will be an input output system that will be required, for example the display uh, or monitor or various other things, right? And you also know that okay, there is a memory which will be required. Then I don't know how many of you know that the concept of cache, but just to briefly explain what that cache is. So basically the frequency at which your central processing unit operates, and what at which the memory operates or data transfer from memory happens, there is a quite a lag. And to bridge that gap, there is an intermediate memory, you can say, which is named as the cache. So those are some of the intermediate memories between the main memory and the central processing unit. Right now, there are also multiple level cache like L1, L2, L3, which are again part of the CPU nowadays. And as we saw that okay, there could be also some of the users are doing gaming with that, so you might need a specific graphics processing unit, right? And now I will just explain that okay, along with the CPU graphics processing unit, the other things which you will need is a memory controller, right? So now what you see here, like different components are named, and you do have the interfaces for that. Okay, so if you think from the what this Intel processor will consist of, so this Intel processor, apart from the CPU cache, what it will require is the controllers which can commu- communicate through to these devices through these interfaces. Okay, again I am repeating. So if you think from this what this Intel processor will consist of, so we already know about the central processing unit or graphics processing unit or cache and all, but along with that what it will require is to have the controllers which can communicate to these devices through the interfaces which are mentioned here in the platform, this diagram. Okay, so for example, if you want to communicate to the system memory, you need to have the DDR controllers. What is DDR? Is it's basically double data rate. It's one kind of you can say the industry standard that requires that sets the protocol how to communicate to the memory. So you will have this interface, right? And then you need to have the controller inside the SoC or microprocessor which can communicate to the system memory through this DDR channel A, channel B. Similarly, if you go for the next component here, it's SSD drive, which is basically the solid state drives, storage device, right? Now, if you see what is the interface here, so it's basically PCIe SATA. So PCIe is again like if some of you know that it's basically peripheral component interface express. Sorry, peripheral component interconnect interface. So these are some high speed interface, right? Or it can be connected to the SATA. Now, if these are the interfaces you need to connect to the SSD drive, what you need here is a PCI controller or SATA controller. Most of us have used the USB. We have USB stick. We have USB based headphones, or there are also USB based displays and all. So you can see that, okay, maybe to connect to those USB ports, you have the USB 2.0, 3.0. These are again industry standards. So you need to have the controller inside this microprocessor, right? So similarly, you can see that, okay, some of the important components, we have Wi-Fi, which again is sitting on the PCIe. There is a near field communication, NFC. Then there is a Ethernet. Then you may have the modem 3G, 4G, or you may have Bluetooth. So these all are, so Bluetooth 3G, 4G in this case is sitting on USB 2.0. Wi-Fi again sitting on PCIe. Then I mean the Ethernet, NFC or SD card slot is sitting on PCI Express, right? Now, another one of the important components which you might be aware about, the sensors, right? Most of the modern computers has lot many sensors today. For example, gyroscope or global positioning system, GPS or magnetometer or touchpad or accelerometer or ambient lights. There are many others also, right? So these are some of the slow peripheral devices, and some of the interfaces which can be used to communicate to these kind of devices is like I2C, UART or USB. So there are some of the interfaces we can connect through these sensors. And again, you need the controllers for either I2C or UART or USB. By the way, I do have a last reference page where like you can go to understand which all these interfaces are, and what these all mean for. Some other components again like fingerprint sensor or touch screen or trusted platform modules. Now this is used for the encryption and all. You do have BIOS or firmware. Then you have cameras. Then you have embedded display port. Again, this is one industry standard for the display ports through which you can connect to the panel self-refresh ports also. So panel self-refresh is another technology where like when the content is static on the display, you can turn off the interfaces. You can also turn off the display controller so that you can save lots of power. So this provides some kind of additional power feature. Okay, and then you have the legacy digital display interface. So I think this slide, what it talks about, what all the components which will be which are there, which makes a platform. Again, this keeps changing. The newer generation may have more components added. For example, in this you don't see the HDMI, but if you go to the newer product line, you will see there is a HDMI, there is a Thunderbolt. So these are some of the new interfaces which are being defined, and it can like have more flexibility in kind of devices or high speed devices which you connect. So it gets evolved, keeps evolving, right? But this is the basic concept actually. Now if you think from the platform perspective, you have these hardwares, but then you need to have the drivers for these, or you need to also have the firmwares for this, right? And then to utilize this, you need to have the other software. OS should have some kind of implementation. So there is so many components which require to have some changes to support all of these, and they needs to be optimal for power and performance. If they are not, and usually they are not, I mean, your power and performance could be quite bad. And what we do is to optimize all these components, whether it's a hardware, software, or interfaces or whatever, so that what comes to you is optimal in power and performance. Okay, so now let's go to the simplified power equation. Okay, so we have seen there are so many components in the platform, like we have the CPU, we have cache, we have memory controller, we have other controllers like USB controller or SPI controller, or UART controller or I2C controller. Then there will be some interconnects also, which connects all these devices which are inside SoC. So there is some generic equations which has been provided, I mean, for these electronic circuits. And so in general, there are two components of the power when these electronic devices are powered. Uh, one is basically which we call it as the dynamic power. So that depends on if a circuit is running at a some specific frequency, then it has some dynamic component of the power, which basically is the first part of this equation. The second part of the equation is the leakage or static power, which we will not discuss in detail here. So even though, let's suppose you assume that okay, you have a circuit, but you have not provided any clock to it. So you have not provided any clock to it, so it's not actually operating. But if most of you must be knowing that the basic block of all these electronic circuits are transistors. And in transistors, even if you have not supplied or connected any clock, but if the voltage, supply voltage is there, right? If the supply voltage is there, what eventually will happen is there will be some leakage current due to the minority carriers, right? I don't want to go into more details, like you need to understand the VLSI, some of the VLSI concept like CMOS, PMOS and all, but I will just briefly tell that okay, the minority components for the NMOS or the NMOS could be your holes, and majority carriers could be electrons. So maybe once you will go into the higher classes and all, you will understand more on that. So but in briefly what I have talked, that even though you don't have any clocks, but because of the supply, voltage supply and all, and because of the presence of some of the minority carriers and temperature and some of the other ambient conditions, you may still have some leakage, or which we call it as static power. But today we are not going to discuss on that. We'll talk more about the dynamic power, which is the first equation. And if you see first equation, what are the different parts to that? So power equal to, or power is directly proportional to half of F into A into C into V square. So let's see what is this different F, A, C and V. So F is the operating clock frequency, right? Then C is the capacitance, and it's basically constant once the processor is fabricated. So once you get the die or IC, usually that capacitance is constant for a given electronic circuit. Then you have V, the operating voltage. I think you must be knowing that okay, these electronic circuits either working at 3.3 volt or 1.8 volt or 1.2 volt or lower voltage. So those are some of the operating voltages for these kind of electronic circuits. And A is the activity factor. Now what this uh, activity factor means? So and I think briefly I will touch upon that because you should understand what this activity factor means. So I don't know how many of you, and most of you must, if someone is using the laptop, you must have used the sleep button, or sleep button. We also call it as S3, platform S3 state. And you must have also used hibernation, right? We call it as S4 or something. So let me just briefly touch upon what this activity factor is about. So when you are running some program, or if you are doing some activity on the CPU, what happens? Your CPU and its or the other components of your microprocessor is active, right? Now there are different low power modes are defined for the platform. Okay, one of such is sleep or S3 button. So what happens when you press or you go into the sleep? What happens? Let's suppose, so this is my current work which I was doing, that okay, I have opened the Zoom, or I might have opened some of my browser pages or something. So what happens, the context of that, and when I'm saying context of that means you can say the starting addresses of that, what happens, gets saved into memory or DRAM. Okay, and rest of the circuits, which includes your CPU, or also includes cache, or it also includes most of the uh, controllers which we talked about, like I2C, USB, most of them, except maybe few wake logic. For example, if something came on the WLAN, some important message came on the WLAN, so you want to wake up, or something else, which is basically configured that you press one button and then it should come from the sleep state. So some wake circuit will remain on, and rest all will get power gate, right? Again, I'm just saying, so sleep state, what happens, most of these contexts of these applications will be saved on the DRAM, and rest all will be power gated. Now think about this equation what we have talked about. So we have talked about two parts of this equation. One is the dynamic part, which is the first component, and the second one is the leakage component. We talked about the dynamic part comes into the picture when there is a operating frequency. Okay, the other part we talked about is the leakage, right? Now in certain conditions, the first equation, we are talking about the activity factor here. And you think about that, okay, if your system is not activated, it can go for the in the power gate state. Now in power gate state, what happens, basically your connection of these circuits to the supply can be disconnected. Okay, because it does not require to work at that point of time. So if the connection to the supply is also gets disconnected, which is called as the power gating state, what happens, you don't have any supply, so even the leakage or static power will not be there. Okay, so your first part, which is the dynamic component, will be zero. The second part, because you don't have the supply anymore, that also will become zero. Okay, so your entire system power ideally will be zero, except the memory power and also some of the wake up logics which is required. Okay, now let's talk about what this DRAM is, right? So the DRAM is again a volatile memory, right? So what does that mean is that once you store something in the DRAM, it remains there till you keep its power up. If you power get the DRAM, whatever is there in the DRAM, it gets lost. Now there are non-volatile memory which are usually secondary storage like disk and all, SSD or hard disk and all. But in this case, which was sleep state, we are keeping all the things in the DRAM. So you need to have the power supplied to the DRAM at a rate which is required by the DRAM and also called as the memory refresh latency. So it needs to be refreshed at a certain refresh rate. So the so that much of power will be still be consumed. Okay. Now think about what happens in the hibernation. So now in hibernation, what happens? All of your contexts of your applications get saved into the secondary storage. So whether it's a hard disk or whether it's a SSD, now the advantage of those secondary storage is that it's a non-volatile memory. You can turn off the power and whatever the content is there, it can still be there. The downside to that is that once you come back from the hibernation, the time it will take to come back when your applications are back to their normal state or previous state will be more than when you put it in the sleep state. So you have added extra latency, but then you saved more power. So in the case of hibernation, you will save more power than in sleep, but the latency to go back to your previous state will be more. Okay. So this is what the activity I was just trying to explain what this activity factor was. So in this case, for example, sleep state, you still have some activity factor for the DRAM. Okay. But in the case of hibernation, the activity factor for the DRAM is also 0. Similarly, each electronic component, for example, CPU, can be on for some time when it's required and can be turned off when it's not required. So whenever it's on or active, or the percentage of time it will be active for a certain period of time, that's called as the activity factor. So if suppose activity factor is 0, that means all the time it's off. Or for a certain workload, let's suppose I'm doing something on the modem side and my Wi-Fi can be turned off. So the activity factor on the Wi-Fi can be 0 when I'm doing something on the modem side, right? So now these are some of the concepts we use, that there will be some of the power islands which will be defined, that okay, there could be some use cases where some of the components will be on but some of the others can be turned off. So the components which can be turned off through some power delivery mechanism or some power management mechanism can be turned off, and that can be saved, right, through this equation. So uh, if for a certain workload, if a CPU needs to run only 50% of the time, so your activity factor is 0.5. Okay. We already talked about the operating frequency, capacitance we talked, and voltage. Now if you see this equation, coming back to the dynamic, the power is directly proportional to the frequency. And now let's go back to that concept that if we operate at the higher frequency, my power consumption will be higher, or actually it will be linearly higher when you increase the frequency. Activity factor, again we saw that okay, it will be again linear. If it's turned off, it's completely off. Now voltage, if you see, it's proportional to square of the voltage. So this is one of the important things here, that the savings or reduction in the voltage will give you square of the saving in the power. Similarly, if the operating voltage gets doubled, your power will be 4 times. So because it's a square proportion to that, right? So voltage is very sensitive. And I think I have not explained you the Moore's law here, but if some of you are already I mean like going through some of these articles and all, you must be knowing that okay, Intel is currently at the 10 nanometer node, right? So our current generation of products are there on the 10 nanometer node. And in general, the Moore's has given a law that every 2 years, the number of transistor on a given area will get doubled. Now, how that gets doubled? Now that gets doubled by going to a new node or new process technology every 2 years. So for example, previously we were at 14 nanometer technology. Before to that, we were at 22 nanometer technology. Before to that, we were at, let's say, 32 nanometer technology. And in general, this should get advanced to a new node technology, let's say from 10 to 7 to 5 to 3 to whatever in 2 years. But that's, so that was what the Moore said, that with that you should be able to double the count of the transistors in one area. Now with that scaling, when you reduce the size of the transistor or channel width of the transistor, there are other advantages also comes. For example, your operating voltage can come down. So if it comes, let's suppose if it's reduced by half, then you can think that, okay, how much your power will get reduced. So power will get reduced by 1 by 4, right? Because zero point 0.5 square is actually 0.25. So that's the advantage once you are able to reduce the operating voltage. So some of the techniques which we talked about, that, okay, can you reduce the activity factor? We talked about that, okay, can you, if you want to reduce the power, can you operate at lower frequency and go for the higher frequency only once it requires? Okay. Then similarly, can you lower down the voltage? Now, one of the important power optimization techniques is called as the DVFS, dynamic voltage frequency scaling. So what happens? So for example, let's suppose you want to run something on 4 gigahertz. Okay. And or your workload or what you are doing demands to you to run at 4 gigahertz. Okay. Now, in order to run at 4 gigahertz, there will be also a requirement for the operating voltage. Say that to run at 4 gigahertz, you need to, let's say, operate at 1 volt. Okay. Uh, Now your demand has gone down, and now you can operate at, let's say, 2 gigahertz. So when you are operating at 2 gigahertz, the requirement to run at 2 gigahertz maybe, let's say, 0.8 volt only. Okay. So whenever you need to run at 4 gigahertz and the requirement of the voltage was 1 volt at that point of time, so what you need to do is, first you need to increase the voltage to 1 volt and then increase the frequency to 4 gigahertz. So voltage needs to be increased first, and then the voltage will increase. Sorry, the frequency will increase. Now, when you are going down the frequency, what happens? You can reduce the frequency first. So for example, from 2 gigahertz to, sorry, from 4 gigahertz to 2 gigahertz, you can go first, keeping 1 volt initially, and then you can ramp down to 0.8 volt, which was required. So now you think that when you are running in the lower frequency, it's not about that you are getting a benefit because of the linear scaling down of the power from frequency, but because you can operate at the lower frequency, you should be also able to reduce your voltage. And once you are able to reduce your voltage, you can get the benefit almost square, right? So and this technique, basically we call it as dynamic voltage frequency scaling. So you go for a higher frequency only when the load demands that. If the load does not demands that, you go to a lower frequency. How you know that, okay, whether the load demands that or not? So you keep monitoring your CPU utilization. For example, you are doing some task at 2 gigahertz and you found that, okay, your CPU utilization is 90%. Okay, so you bump up to maybe 2.4. You found that, okay, still it's at 90%, you can bump up again. Or you can have various other governors, which we call it as governors, to see that, okay, if there is a app launch happening, you were at 2 gigahertz, you can directly go to 4 gigahertz because it's an app launch, right? So there could be some different policies to give you a performance boost, and when the work is done, then you can go back to a lower frequency to save more power. Okay, so I hope that, okay, briefly I touched upon the different techniques. I have not gone into too much detail into all of this, but I think this should be briefly explaining what is there. Okay, so now once we talked about the simplified power equation, let me go to the power distribution of the components. By the way, I have not talked about how we do the platform power measurements. So I will just touch upon that. Okay, on all these reference validation platforms for all these components, there will be a series power measurement register. Okay, and these registers will be monitored for the differential voltage. That means what is the potential drop into that registers, and uh, and you can also monitor and you know what is the sense register value, so you can get the current from that, and then you can always multiply with the voltage at that point and you can get the power. So so for all of these components you can keep monitoring this power, and then for a workload for a long time average, let's suppose 10 minutes that workload is running, so you can take an average and get the average power for that. Okay, so now let me just try to explain you. So we talked about there are many components, but which all these components usually consume how much of power for a certain workload. And I have not taken many workloads here. I am just going through a very simple workload which is called as the static content on the display. So many times you might be you might be doing something on the desktop and then be idle. So for example, in this case you can see one of my file is just static. There is no change in my content, right? When you are playing video, the content is changing. When you are doing some browsing, it's getting refreshed, so some changes are happening. But most of the time when you're, let's suppose the background screen is there, or OneNote is open, or PDF, most of the time you will not doing anything. It's just idle. There is no change in the content on the screen, so it's called as the static content on display. So think that, okay, which component could be taking the maximum power? And if we just see based on some of the data, we find that, okay, display, which consists of the panel electronics power, backlight power, and touch, consists of almost 55% of the total platform power of static content on display. The second one is the application processor. So this application processor is nothing but, for example, in this case, it could be Intel microprocessor, which consists of CPU, graphics unit, imaging processing unit, or DDR controller, or various IO hub like USB controller, I2C controller, SPI controller, and many more. Or by the way, power delivery systems also could be there. Okay, so this power delivery chip, what is this actually? So I don't know whether you have seen, or maybe if you are using a smartphone, you might have seen that your operating voltage of the most of the smartphone batteries will be around 3.8 volt or 3.7 volt. But all of these I mean the circuits may not be operating at 3.8 volt. Some of them may require 1 volt, 1.2 volt, or 3.3 volt, or 1.8 volt. So you need converters. You need converters which can convert 3.7 volt to these voltages, and some of those are either called as the voltage regulators or LDOs. Okay, so that this power delivery chip is like combination of all these voltage regulators and LDOs, which consists almost like 50, takes 15% of the total platform power. Then the memory takes almost 5% of the power. Then storage takes almost 22% of the power. The communication side, like whether it's 4G, Wi-Fi, BT, NFC, GPS, almost 2%. Then sensors, which are like, there are many, but overall those are quite power managed, and it takes just 1% of the power. So this is a distribution of the power of a platform, and display takes more than half of that power. Then you have application processor, then power delivery chip, and then rest of the things like memory, storage, connectivities, IPs, and sensors. Okay, so yeah, I just wanted to show that, okay, different components may take different powers, and that's why we need to ensure that, okay, these components are taking only that much power as it required, or is optimal in the design, or their drivers are optimized, or their firmwares are optimized, or the way things are implemented is proper. Otherwise it may happen that, okay, your display power is much high. For example, in the case of display, you might have observed that when your background is black, your panel power your backlight power can be modulated and it can be low. But if suppose that is not working, your actual display power can be quite high. I think those techniques, some of those techniques are either called as the keyback or DPST in case of Windows. In case of Android, it's called as keyback. Okay, so I don't know how much time is left for me.
Sir, you have ample amount of time.
Okay, thank you. Okay, so we'll go to the last section of this, which is basically battery life calculation, and I hope some of you also can do some exercise with that. Okay, so we'll go to the last section, and why I have taken this section is basically this is one of the important aspects of platform power and performance engineering, that you want to optimize the battery life of a given workload or use case. For example, how much is the battery life when you are doing a video playback, or when you are doing a browsing, or whether you are in standby. That is finally depends on how much power is consumed during that workload or use case. So it's important for us to understand what is this battery life calculation or spec about, right? And so that once you have this data, you can have some data from the competition side also, and then you can work with your engineering team to come up with the optimizations plan, or what should be your right battery life for these kind of various use cases. Okay, so in general, what happens, we saw that there are two kinds of specifications which comes with the these devices. uh, so for most of the small form factors like smartphones or the tablets and all, you can see uh, the rating will be given in milliampere hour. Okay, and if you go for a larger form factors like laptops or twin ones or converged mobility products and all, you can see it's still in the watt hour. Okay, uh, so we'll explain both of these. What does this mean? uh, so just to briefly touch upon that, okay, once you, if you see the specification is in milliampere hour, let's say if it's a 1000 milliampere hour, what does that mean? So what does that mean is that if you consume 100 milliampere current consistently, your battery will be over in an hour. So if you are consuming 1000 milliampere hour consistently, you will finish your battery in 1 hour. The other specification you might see that, okay, let's say 50 watt hour. What does that mean? So if you consume the power of 50 watt consistently, your battery will be over, or will be empty in 1 hour. So that's the way this specification comes with these all devices. Okay, so I've just taken one example from iPad for battery life specifications. So this is one non-removable lithium polymer 11560 milliampere battery, and I think the right side 42.5 watt hour is not given. 3.7 volt will be given actually, but I think 42.5 watt hour is not given. Maybe we can just do a quick math on why that 40, or from where this 42.5 watt hour will come. However, so as I said earlier, 11,560 milliampere hour battery, what does that mean is that if you are consuming 11,560 milliampere continuously, your battery will last for 1 hour. Okay, now how to convert into the watt hour, right? So if you see, milliampere is in current, watt is power, right? And if you see the equation of the power, it's basically P equal to VI, that means the voltage into current. Now these smartphones like iPad and all, the if you see the battery specification, it will give you the average voltage of 3.7 volt. In general, the operating voltages will be around 4.2 volt when it's fully charged, to maybe 3.3 to 3.2 volt or 3.4 volt when it goes into the dead battery zone. And on an average, its average voltage will be 3.7 volt. Okay, and I said you that, okay, you can easily convert the current into wattage or power if the voltage is given. So 11560 milliampere will, if you convert into ampere, it will be 11.56. and that you multiply with 3.7, you will approximately get around 42.5 hour. So the 11560 milliampere battery specification is equivalent to something like around 42.5 watt hour. So with that, if you understood, let's go to the understanding some of the specifications. So if you see the iPad for battery life specification, you may see it's written talk time up to 9 hours or standby time up to 720 hours. Okay, and again, by the way, this is a tablet. So, and one of the use case was the like voice call and all. That's why I think talk time is one of the important use case. When you go to the laptops, you will not see talk time as one of the use case. Then there are other use cases also specified, like up to 9 hours on cellular network. So that will be mostly the modem side. You are connecting through modem, and if you are connecting through Wi-Fi, it's around 10 hours. So these are some of the specifications you can find if you purchase an iPad or if you search online. Okay, now let's try to understand that what does that mean for that use cases, how much current or how much power is being consumed for while you are talking or while you are doing nothing. That means it's a standby, or when you are using internet, either using modem or maybe using Wi-Fi. Okay. Okay, so battery capacity given is around 11,560 milliampere hour, and let's I is the average current consumed in standby in milliampere hour. Okay, so battery life and standby is 720 hours. I think let me quickly go to the last page. There we had given standby time up to 720 hours, and that is what we are trying to decode. So this is the specification given. Battery capacity is 11560 milliampere hour, and battery life in standby is 720 hours. Okay, and as I said you that what does that mean, that if you are consuming 11560 milliampere current, that means you will last for 1 hour. Now here what I am interested in to find out the average current during standby, right, so that it's lasting for 720 hours. Okay, so that means the way I should equate is that 11560 milliampere hour into, or it should be equal to current consumed during the standby, right, into 720 hours. So that gives you the same energy basically, right? And if you use this equation, you should be able to find out what is your current. So your current comes out around 16.05 milliampere hour. That's around 16 milliamps. By the way, if you are able to calculate what's your current average current consumption during the standby, you should be also be able to find out what is the power, given that you already know that the average voltage for the battery is around 3.7 volt. So assuming battery average operating voltage is 3.7 volt, so power in standby is 16 milliamps into 3.7 volt equal to 59.2 equal to around 59 milliwatt. Okay, so I hope that okay everybody got how we are converting that specification into what is the average current consumed or average power for that workload. So so in general what happens once you are able to get this power, this is your target for the platform power and performance engineering. That means all of the components which we talked about, whether it's display or the application processor or memory or power delivery or connectivity or this and that, should add up, and it should not consume more than 59 milliwatt, or it should not consume 16 more than 16 milliamps. So that becomes your target for that product, and that you need to deliver through the platform power performance optimizations, right? So that's why we need these kind of calculations. Again, just a recap how we calculated. We know that what is the battery specification, which was basically 11,560 milliamperes per hour. We know that what is the battery will last for standby if I'm only using the standby use case. So if I use the same current So it will last for 70 to 720 hours, and that should be equivalent because the capacity of the battery is same. So whether you burn 11560 milliampere hour for 1 hour, or whether you burn something for 720 hours, the capacity of the battery remains same, so it should be equal, right? So with that you are able to calculate the current, and you know the voltage, you should be able to calculate what's your power. Okay, maybe I will just give one more minute here so that you are able to understand how to calculate, because the next I will give you some tasks to do. Okay, so so I think two use cases we just left. It was the voice call or browsing on Wi-Fi. So, and use cases battery life were given 9 hours or 10 hours. So I want you guys to just do some math and give me the average current and average power in milliwatt and average current in milliampere for these two use cases. Again, I will just give you the equation that we need to use. So you know the battery capacity was 11560 milliampere hour, that you need to equate with the current of the specific use case into the battery life in hours. So once you equate, you should be able to calculate the current for that use case. And to get the power for that use case, you should be able to just multiply with 3.7 volt and get the average power in milliwatt.
Once you get the answer, students, just raise your hand and I will unmute you. Okay? Okay. Ayush.
Yes, ma'am.
Yeah.
Ma'am, this sir has said that electronic circuit basically works on 1.5 volt or 1.7, I think so. Can electronic circuits can work on 5 volt or more than 5 volt or 12 volt?
I'm not getting that point.
Sir, you have said that electronic circuits works on 1.5 volt operating voltage.
It's not 1 volt. It depends on the technology. For example, CMOS can be different, TTL can be different. And for example, like most of the CMOS technology right now, some of the operating voltage could be around 1.2 volt. So it's not that okay, it operates at the specific voltage of 1.5 volt or something like that. Also, it depends on what frequency. So there are many constraints and things which dominates to tell that what will be the voltage. Certainly not in 12 watt 12 volt range nowadays. I think not even
Okay.
before. Yeah.
Sir, if we are working in Arduino, if we are working in Arduino,
Mm-hmm.
so can we work on 12 volt? Can we
So
work?
you can provide 12 volt provided you have a converter after that which can convert into the specified voltage. So you need to know, if you are using an IC, you need to know what is the required voltage for that, right? I think that specification should be provided in the IC. Now, if you have a 12 volt as an input, you need to convert it into the specified voltage. So you can get the converter ICs, okay, which can convert maybe from 12 volt to 1.2 volt or 1.8 volt. Now, what is your specification of the IC? What is the operating voltage that you need to find out? I don't know what exactly you are doing, but you should be aware about the what is the required operating voltage for that IC, and whatever that required voltage can be converted from 12 volt to that with some of the converter ICs which are readily available in the market, maybe
Okay,
from
thank you, sir.
TI or something else. So meanwhile, can you just yeah, try to solve this problem and give me 1 minute actually? Is that okay?
Yes, sir. Yes, sir. Okay, students, calculate. And if you get the answer, just raise your hand.
Hello.
Yes, sir.
So maybe I think I can just go quickly if the people are ready.
Yeah, but nobody raised their hand. I guess they don't have the formula with them, so they didn't
Okay.
calculate.
Okay. So I think, yeah, maybe. Okay. So I think formula was just we need to just let's take an. So for example, voice call, we talked about, okay, the battery life is 9 hours, right? So the let's assume the current during the voice call is I. So I into 9 hours would be equivalent to, sorry, the current for voice call is I milliampere. So I into 9 hours would be equivalent to 11560 milliampere into hour, right? So once we equate, we should be able to find out I. So I will be 11560 divided by 9. So if we, sorry, somehow I'm not able to change my, okay, yeah. So these all are the currents, and then you multiply with the voltage, you should be able to get the average power. Okay. So I hope like someone is able to get these numbers.
Yes, I can see few answers in the chat, and one a student has raised his hand, Aditya. Let me unmute him. Yes, Aditya.
First of all, good morning to all.
Good morning.
Yep,
Uh,
yep.
Ma'am, the answer for voice call one is when we multiply I with 9, that would be equals to the battery life, like,
That's
and
true.
the answer for that would be approximately 1284 milliamperes.
Yeah, makes sense. Like you can see here also on my screen,
Yes, sir.
it's the same number, and I think you
Yes, sir.
got
I
in
am
milli.
getting the same number, sir.
Okay, you converted into the milliwatt also.
Yes, sir. It's 4277.2, which is equivalent to 4277 milliwatt.
Okay, that's cool. That's cool actually. Okay.
Thank you,
And
sir.
Rashmi. And Rashmi.
First of all, good morning, sir.
Yeah,
Sir,
very good.
for browsing on Wi-Fi, battery life is 1156 milliampere, and
Mhm.
power is 4277.2 milliwatt.
Okay, that's cool actually. Yeah, very good, very good. Yeah.
Okay. Thank you,
Okay, so
Rashmi.
yeah, we have good answers here. Thanks for the active participation.
Yeah.
Okay.
And Raksham also? Raksham, I'm unmuting you. Yeah.
Yes, ma'am. Sir,
Yeah, go ahead, Rakcham.
Sir, I have just a general question.
That would be Raksham. That would be taken in question answer sessions shortly.
Okay,
That would be
ma'am.
shortly. Okay.
Okay, ma'am.
Okay.
The-
Okay, so I think, yeah, I mean that was pretty good actually. So you guys understood the concept, how to calculate the battery life or get the corresponding average current and then convert it into the power, and that's basic your basic power and current requirements for that use case, which we engineers basically optimize that use case for. I think, yeah, I mean that's the basic. I have just given some more exercises for the laptops, and I think maybe I will just skip right now this one. Maybe we can go for the question answer session.
Okay. So
Yeah.
now the question answer round is open. Anybody who has any question can raise their hand. Sir, if you okay, you will be needing your screen to be shared.
Okay, sure.
Okay. So Raksham, I'm unmuting you. Yes, Raksham.
Sir, my question is about that. I've been using many Apple products like in iPad 4,
Mm-hmm.
right? Released in 2012, right?
Mm-hmm.
So in the iPad released in 2012, having the battery capacity of 11,000 mAh, right? And
Mm-hmm.
right now the recent iPads which are released right now, the iPad Pro and all, they are having battery capacity below 11,000, more likely 10,700 or 9,900.
Mm-hmm.
So is it that they are advancing their chemical?
Yes. No, 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 no. It's not about advancing the chemical. It's about like optimizations on the use cases. So, for example, you have seen that okay, maybe standby they were consuming 16 milliamps. Now they might be consuming 10 milliamperes. Similarly, if we saw that okay, Wi-Fi they were consuming around 1156 milliampere, right? So they might have optimized further maybe 20-30%. So see, I mean, like how, what should be the battery capacity? I don't want to use a battery capacity, large battery capacity, because that means I need to have more cost. So my, to minimize the cost, my intention is to use as less battery size as possible. But to do that, what happens, I need to reduce the power consumption. So that is what it is, right? And most of the like microprocessor vendors, like whether it's
Yes, sir.
Intel, Qualcomm, or even tries to minimize their battery lives or basically the power consumption for specific use cases. So Apple is one of the very good like the brand name which does lots of battery life optimizations for these use cases or KPIs, and which in turn helps them to reduce the battery size and increase their margin on the products. So because it reduces their cost of you can say the device. That helps you to understand the
Yes,
how.
sir.
Okay, cool.
Yes, sir. Thank you, sir.
No problem.
Any other question? You may raise your hand apart from these.
Can I have a question here?
Yes, ma'am. Yes, ma'am. You
Yes,
can.
sir. Okay. Sir, good morning. This is
Mhm.
Dr. Asta Sharma.
Very good
And
morning.
I had a question like today we are like exploring this energy harvesting solutions for improving batteries and for power one. So
Mhm.
what Intel is working upon it? Is it exploring this domain?
Energy harvesting.
Yeah.
Maybe if you can explain like what exactly that, maybe I can give you more inputs on that.
Energy harvesting, like a concept is to harvest energy from environment. There can be many sources like solar, wind,
Yeah,
and
yeah, got it.
uh,
So I think, yeah,
forest.
I don't think so right now we have any viable commercial plan on that. Some of these things will always be there in the R&D, but I think it comes into the product only once it becomes a business justified, when it makes sense that okay, we'll be able to earn money with that. So many of the R&D definitely happens in all these things, like can we just get some energy from the heat which is getting generated while we do some work. And there are many things, we have many sensors and all, but as I said, that unless it's a economically or business viable option, it's not right now in any product line, at least in the client segment.
Okay, great. And like I was seeing that processor diagram where there were like 4G, 3G, we were seeing that peripheral was there.
Mhm.
So what about like 5G and what advancements would be required in 6G if we go in the processor?
In the 5G,
Yeah, 5G, 6G, as we are advancing the generation. So in the processor, what will be the improvements? Can you like cite it so that we can understand more about the hardware part or processor part?
so in general, if you see from the network, I mean like the 5G perspective or whatever, mostly from the processor requirements side, we don't have any specific requirement. Specific, maybe some specific requirements are there. For example, coexistence with the WLAN, that how the 4G or 5G modules can coexist with the WLAN. But any specific requirement on the processor side, I don't remember that. Okay, we have worked on that.
And Dr. Asta, you are asking about 5G spectrum,
No,
4G
no, no.
spectrum, or the generation of the processor?
Okay, okay, great. Okay. Thanks for clarifying it. I was asking for the evolution, like when we are going for
Okay,
5G, 6G, so how
right. In
that advancement?
communication.
Yes, 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 yes.
Okay. But I guess sir understood about the generation of the processor.
Okay,
Yeah, so I think
okay.
yeah, I was giving more talk about the microprocessor, but as I said that okay, there are some specific requirements, not like so. So whatever the 5G or 4G throughput related, latency related, whatever some of the requirements will be there, right? That will be definitely there. But in general, most of the things will be taken care from the modem side itself. So we do have a modem chip. For example, currently we have the 756X series, and 5G. Anyhow, I think we have sold our modem business to Apple. So 5G we will have only in the networking side some of the solution. But so most of those networking related solutions will be, or the capabilities will be available on the modem chip itself. There will be some requirements which will be tied to the microprocessor. For example, in this case, how we can coexist with the high speed DRAMs or WLAN. For example, when we are operating at very high speed and all, there could be interferences and all coming in the DRAM or WLAN, how you can coexist. So those kind of interfaces or requirements at the platform level will be taken care in the next generation platforms. So that happens. But rest of the things, I think the chip, the modem chip itself takes care about.
Okay. Okay.
Okay. Thank you, Dr. Asta. Any other question? No, no question. Saurabh, you unmuted your mic. No, no question. Okay, then I guess this should be the end of this fabulous session. And I really want to thank you, Asit sir, for your valuable time and insight on this topic.
No problem, my
And
pleasure.
yes, sir. And in this lockdown where everybody is struggling, I think sharing of knowledge is one of the, you can say, the lightning which keeps us going. Thank you so much, sir, for the session.
It was my
Thank you.
pleasure. Hope it helped some of the students which are in the session.
Yes, surely. Okay, now we'll be starting our next session, and that would be taken up by Dr. Daniel Hahn. Astha, Dr. Astha.
So I will drop.
Sir, you can,
Okay.
but if you want, you can attend the session as well.
So I will have to drop. Actually, I have some other work, so maybe I will drop. And thanks a lot for giving me this opportunity, and hope that we can again come together sometime else.
Sure, sir, sure. Okay,
Okay.
thank you
Thank you
so
very
much,
much.
sir.
Yeah.
Dr. Astha, over to you.
Okay. Thank you.
Dr. Asta, just a second. I would like to
Okay.
request everyone to please switch on their video for a minute, please, because I have to take a screenshot. Can you?
Okay.
Karan Rawat. Okay, got it. Thank you. Now you can switch off the video. You can switch off the video now. Dr. Astha, over to you now. You can
Okay.
introduce our eminent guest, second eminent guest.
Yes. Sure, ma'am. So, good morning, all. It is a great honor for me to introduce and welcome our guest speaker, Dr. Daniel Hahn, for today's session. He is an accomplished professional in the field of automation. Presently, he is a senior expert at Steinberg's Advanced Risk Management in Stuttgart, Germany. Daniel Hahn studied mechanical engineering at the Technical University Aachen. In the year 2001, he joined APS, European Center for Mechatronics, as a research scientist up to the position of CEO. At APS, he successfully accomplished several national and international projects. In 2007, he received his PhD in the topic of robots in a workshop-oriented production for small batch production. Dr. Hahn participated in the three lighthouse projects, OSIRIS, EU Socrates, and IMC AESOP, in cooperation with companies like ABB, Schneider Electric, Siemens, ARM, Jaguar, Honeywell, Thales, and SAP. The successful completion of those projects paved the way for the introduction of Industry 4.0 in 2012 at the Hanover Fair in Germany. He is an eligible guest at international conferences and workshops all over the world. So Dr. Hahn was many times invited as a guest of honor and keynote speaker at many international conferences. Daniel is an expert in collaborative project of the World Bank and the MSME Ministry of India, guiding Indian technology centers to new ways of production. Further, he is an active member of the Electronic Sector Council of India, paving the way to industrial automation in India. Today, we are privileged to have an opportunity to listen to him. On behalf of all participants and all, I welcome you, Daniel, sir, to this summer academic internship program on automation. So, yes, sir.
Okay, am I audible already?
Yeah, yes, audible.
Okay, so how do I now switch to the camera?
Sir, your camera is on and I have made you the co-host. So you can share your screen also if any PPT is there.
So can you now see in the back the television?
So television can be seen, but it is quite small. It is in you are actually coming in a tile. Your link is coming at a tile size. So, sir, are you on any laptop or mobile? You can run
I'm
your.
on laptop and behind me should be the big screen, so you can't see it.
Actually, it will be better if you can like share screen from the same device so that the small fonts can also be visible to the audience. It will be quite cumbersome.
This I do with.
You can share your screen, sir. I have made you co-host. Yes. It is being shared now. Yeah, we can see.
Perfect.
Okay, and I need here.
You can run like slideshow.
We can see your screen,
Yeah.
Dr. Hahn. We can see your screen.
Now there's somehow some. On my screen, strange. Give me a minute here. So the screen as well. How is it? Because
Yeah, it is visible. It is visible.
my machine. So only or as well screen or maybe then I switch off the tablet.
Your audio is breaking, but your screen is perfectly visible to everyone.
Okay, but I need here to change something. Otherwise, my machine is somehow frozen. Don't know why. What happened now?
You can take your time, sir. It's okay. It will be. Maybe system has hanged.
Yeah. So, but yesterday with the Zoom test, but now it is frozen. I stop the videos. Works.
You can disconnect and then reconnect it.
Now it is complete. All is need to. So,
Your voice is breaking, but your screen is clear. It is visible to everybody.
maybe I need to check again if you like.
Can you use mic and earphone? Maybe you are sitting too far off from the source and mic is...
I've
Okay, you have.
oh, and let me need to zoom.
I would like to know its
So it's does it go with
If you have connectivity issue, you can like close your video and can use only the audio platform.
Yes.
now it should be better audible. I change to this mic. Is it now a change?
Yeah, it is a bit more audible. It is...
Okay. So now I changed to this mic. So now it
So,
should be
yeah.
better. Okay, so it's a to be invited again after the HelloCon. So
So your voice is still breaking. Can you please switch off your video and use only voice? Maybe we can get more clear. You can switch off the video and you can play the slide.
so we just stop here like that.
Yeah. Try speaking. Maybe we will get better audio quality.
The mic of the book, but I guess this is not so. So this is Okay, still think
Yes, audible, but voice is breaking.
and this I want to and you can see here that the robot first is checking the right position of it because the task to take the and put them in the cavity. And this was somehow for the students very interesting. There are a real big machine which had been programmed by this strictly remoted. So now again, robotics, automation, everybody is talking about it. What is it really? We want to have a look at it. There'd been industrial revolution, yeah, and usually in the conferences when I'm invited, I ask the students what, and then I ask how was it done, where was it done. Yeah, I cannot really ask you. So the first industrial revolution, it was in England. It came from textile industry. In the of the 19th century, it started a little bit later. This was the first industrial revolution. The second one was then the car production with 10. Yeah, this was the start of production, and then even in the nice the start with C and with even with robots.
Audio quality is not audible.
Industry 4.0, everybody is 4.0. It is defined by like physical system, AI, and we'll have also look to it. So here again, the four industrial revolution, the first powered by water and steam, the second one then even with electrical energy, the third one then with biotechnologies and some progression in autonomous, say, and the fourth one and global trends in robotics, digitalization, and industry for. So here we have a closer look to it. So the fourth industrial revolution, autonomous robots, simulation, some horizontal and vertical system integration, IoT, industrial Internet of Things, cybersecurity, cloud-based services, additive manufacturing, the 3D printers, augmented reality, and big data and analytics. But this is just from research institute. What is the fourth industrial revolution? For example, see augmented reality as a trend from it. So I want to as well warn the students, do not believe everything that's are telling. Not augmented reality. From my point of view, I think this is just a nice method for display data, but not one of the main drivers. So even if they claim to Industry 4.0, I have there a little bit of doubts. So I will sense, dear students, yeah, that is correct. It is somehow to read deeper into it. And now a short history of the robot. Usually, when
Dr. Han,
Yes.
your voice is still
Yes.
breaking. Your voice is still breaking.
Should I speak slow? Is it
Uh,
better if I speak slow, or is it completely?
Speak bit
Is it
slowly, maybe.
completely
There
not
there is a network issue, I guess.
okay?
Can,
Yeah,
uh,
far.
can you change your mic or something? Maybe it can be better.
I'm now on this mic. Now it is on the PC mic. Is it now different? Is it now better?
It's better now.
It is better. Okay, great. So then I put this off. So when you talk about robots, and today often think about more this humanoids. Here from different movies, the robot. This is not we in with industrial automation. What we understand with robots. So, and there are different definitions of a robot, but there is not one only solid definition of it. But the Robot Institute of America, they say a robot is a reprogrammable, multifunctional manipulator designed to move material, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. Oh, wow. That is really a long definition, and even I do not doesn't I like it. They say somehow it's reprogrammable, okay, but then with some variable program mode, this twice this programmable thing. And what about welding robots? I do not see there some welding where it would fit. Then there is another definition from Joseph Engelberger. That's an and he's his life pretty easy. He's saying, I can't define a robot, but I know one when I see one. Yeah, hey, great. A good definition works only when you're an expert. Then you can say it like this. Yeah, if there's an exam, not bring it until you're not skilled as a robot expert. But one, and this I like the most, it says a robot is a one-armed blind it with limited memory, which cannot speak, see, or hear. So again, in exam, should not bring that one, but like it the most. Now regarding history, okay, it started with some mechanical machines, some mechanical automata. So even in Greece and Egypt and some driven machines, but they are for us interesting. For us, it started somehow 61 with the Union and 69 with the Stanford arm. And then it continued with the normal industry robots. What is the difference, automation and robots? Yeah, some automation machines, they're trying to make one single task. Yeah, some clothes washing machine is just for washing your clothes. Some dishwashing is washing dishes. If you put your dishes in the washing machine, then it won't work, obviously. An industry robot, that's a machine which can do a variety of tasks. Do there some weldings, pick and place operations, and so on. Then there are different robot, some walking robots, humanoids, then mobile robots, somehow the robot manipulators in this presentation. So you welding, handling, different joining technologies, polishing, pelletizing, as well processing. So we see here Kia. Kia now is well in south of India. It started 2 years ago. You see here different machines. And obviously, to start such a factory, this requires a lot, and this is why engineers are that hardly not that much required as well in India, because there's much more production starting now in India. Robot, they have 6 axes and can be as well some more. That's a typical one. So it starts the base with 6 axes to the tool, which is then the 6 axes. Then there are industry robots. So it starts with A. This is what the usual 6-axis robot. There are B, cylindrical robots, Gara robots, gantries. This could be even, and Delta robot. For example, the flex figure from ABB, which we will see as well later in a video. Now, one of the topics when we other about robots, often the big question is, yeah, in India, we don't need robots because we have that big population. And first, people should get to work. And then we can look for automation. Why using robots? Because they're in our jobs. We don't need this in India. Yeah, this is something what you can say. But we want to have a closer look to it. And in India, yeah, I heard as well this same discussion we have in Germany as well with automation. Yeah, by using more and more robots in Germany, we have high density, and by using more robots and then unhire the people, so get the, is the future our job somehow that we all get replaced? It will might it come like that? This is somehow big, and all over the world people are, so can we really, yeah, the robot in the end of the evolution, the good old time? Yeah, the big question is, which future do we want? Do we have the robots that us? Look at Japan with society, and they much we do. For example, is this our future? And then if you ask the experts, even they do not know what will be our future. And this is somehow a bit strange, because those experts, which just, so they're not engineers, they look for the social implications and so on, and economics, and even they are not sure how it will work in the future. So some of them, they say it will be all getting great with industrial automation and with robots. There will be new jobs, even if there is jobs, more jobs, they say. And they say, yeah, okay, work will change, but it will be reevaluated, some other or even more qualifications. Yeah. But as well, you have high autonomy and self-organization. Maybe even work-life balance and the face of life-oriented working model. So this means, yeah, I work when I want. Maybe I'm an early bird and I can work in the early morning, or I like to stay longer in the bed and I just start with my work at 10 o'clock, 11. Then maybe I go to the beach in the afternoon, and then I work as well in the night. So why not? And as well, if you have some baby, maybe then you check your working time. So all this is possible. So that's the optimistic view. The view of different experts, that is that the jobs, they will all go, they will go down, so there will be job losses. Yeah. Then as well some polarization of the qualification. Mid skills, they will be somehow, they will be gone. And so this means there are lots of low skill jobs, and then the experts so much in the middle. Then more, Amazon, for example, they have some online tools to control their people. And this is somehow as well something what is now possible in this new world. But is it that good? Because they really control the people and their work, and I think really to even to an extent which might be too much. As well, there's the fear that there is already some digital assembly line work, as well as crowd work. Look at those people who work for Facebook and check the content for some frauds, yeah, for some crimes, and it should be online available. And those have a big problem because in all their working time they get faced with all these criminal things, and they don't get some assistance. So this is as well something what is so nice, and I would not like to work on a job like that. There are a lot of studies, but the thing is they have as well different quantitative methods, and the result which they get is very different. Those experts, they have different views on it, and so how the life will be with all this the new IT approach which we face. So, which is our way? Will be this or a lot? But the big question and is there some compensation so that jobs created? This is somehow in US. They have seen that they say 80% somehow this means is by machines. Only some 5% is somehow some unpredictable work, more difficult to replace. In a pessimistic view, um, there's a lot of jobs which could be replaced. And here's a lot of data all over the world. See India in the on the left side, it is not very much, but this is as well something that I don't understand. I'll do as well a bit about graph because they do not future in automation for India. Yeah, so it's only somehow something like 9% in India. Wonder Indonesia, South Africa, that there is more than this. Obviously, you see very on the top there is Japan as well. Germany is there around, but somehow big question. But example, I'm not so much sure that there's this much automation. So this means for India, is it now the big question? Remember that with methods, they lead to different prognosis. But as you can see as well, some other study that the growth in the labor force in India, it will grow a lot. There will be technology jobs created in India. And as well, they say there is a huge potential increase in production workers in India. Yeah. So although there's a few growth, yeah, what is somehow possible, they see a huge potential in India, and they say McKinsey follows somehow their suggestions. Okay, this is McKinsey, you have to follow them. As well, other who have as well good McKinsey, but they see there's a big potential in India. So this is, and as well, just as when personal computers. So we just heard this interesting presentation from Intel. Yeah, with the course, First, I thought there's not much computers required in the world, but then they had a computer that will destroy a lot of jobs. But then we see, right, retro perspective, that there had been much more jobs created than destroyed. Yeah, so now back to, yeah. So the jobs are somehow lost and gained. Yeah, this will be different countries. And then in the advanced economies like Germany, Europe, US, they say there it will be the largest disruptions. So not in. So what is the future of our work with all the digitalization? And there are different drivers. If we look now digitalization, there's a globalization, there is the transculturation, all the culture which will inflict our life. Um, India has a young which is very good. Yeah. Societies in Japan as well in Germany, people are so there are then issues with the pension funds and so as well in Germany they have the concern that when they have enough money, so this is all possible. Then there's migration, so the brain gain and the brain drain. So East Europe, for example, many people journey as well from Europe. For example, for Italy, not good. Italy faces a lot of in their production, and if the young people, if the young generation, they are to Germany, this is not so good. Then there's a tendency of which is pretty positive to my opinion. Yeah, and somehow the skills is as well good, and this is thanks to um, Dr. Vanna and Asta. Yeah, this is good that there are rising skills and some more academics. So in this century, somehow we have to serve this. Now, what should you do? Yeah, what is the conclusion? One thing for you, especially, never stop learning, but as well with fun and passion. Yeah. Now here, the numbers of new robots which are every year newly installed in the different countries. So in India now, we see 6,000 in 2020 prognosticated. Yeah, they have now the figures only from are usually more than 1 year old. So it's now a lot or not. Yeah. If you look at China, if you know it last year, because those are the figures which we have, in China it was 170,000. And India the last year just 5,000. In North America it's 55,000. In Germany, for example, a bit more than 20,000. Those are the installed industrial robots. For example, one must see they installed as well a lot of robots. For example, the Foxbots at Foxconn. So Foxconn was for the Apple phones, so for the iPhones, and they have robots there. Foxconn their own robots. Those are the Fox. That's how they are called. Well, and some 2-3 ago, they even installed several thousands of robots, but they had not been done because they had not sufficient of engineers for the programming of them. Yeah, and interesting that in the UK there was only 2,300 robots installed last year. So India had even what's than England, the whole United Kingdom. So somehow you see with these figures, it always the question with whom you compare. And, but again, somehow India has just 3 industry robots. Now you see, not about new robots, it's about somehow to do workers which you have. And India has just, we have seen they have a lot of new robots, but a lot of whole population and the workers. This was Germany, more than 300. That's in South Korea, twice as much than Germany. So those are somehow the figures, yeah. The experts from robotics, they say India is having big potential the expansion of the robots industry due to increasing labor costs, more and more automation coming, the increase in production demand, and increasing international competition for producing more accurate. So again, they say that India faces a good future. And the economic time, India can lead the global movement in automation and technology integration. Or what? Now we have seen that India has just some 3 robot 1,000 workers. And now the economic, India can lead the global movement. How that? At the point is it India is that and robots play yeah, so you all know ABB, Asimov, Gray Orange, I guess. Gridbots, Fano, Kuka, Pari, Sastra, or Systematics. And this initiative from Mr. Modi, I'm there as well. You heard from Dr. That I'm there in some boards. And yeah, we had a panel discussion. Yeah, I was in Delhi with Festo, Vibe. Yeah, they look potential for Industry 4.0 in India, and the government they aim to augment the share of manufacturing and the GDP from percent. Yeah. And as well, India is expected to command nearly 20% of the global IoT. This is what your government somehow aims to. So you see that India is doing there a lot. They can grow more jobs in the manufacture, but as well, upskilling is required. Yeah. So in India, automotive industry is one of the main players there. So Maruti Suzuki is one of them. Then Ford in Gujarat, Hyundai, Wagon and Tata in Pune. Bajaj Auto, obviously, but not only factories. As well, they use robots at their factory floors. And some niche as well, domestic robots are estimated to grow rapidly next 5 years. And this is from India. So the big, how to automate with predictable cost. This is as well the question what your government has faced. So, and somehow, why to apply robots? Of robots, there's improvement of productivity and efficiency. and they do not care if there is some holy festival the day before and they are not getting tired. And there's a reduction of the throughput times, quality, obviously, repeatability. They can make always the same movement again and again. This very accurate way. Working for the humans, because the robots can be used in an area where the humans do not like to work. Reduction of hazards for the workforces. Yeah. Then they can be reprogrammed. We have learned by the definitions of the robot, a single-purpose machine like the washing machine, or it's a bottle filling machine. A bottle filling machine just can bottles. A robot would be not so good to fill bottles. Single-purpose machines. But this industry robots we can reprogram, and there might be of material and energy, and again somehow the save of labor cost. That's as well often one of the drivers, obviously. There's some constraints. Yeah, first, obviously, you have to buy the robot, yeah, and cheap. Yeah, sometimes there are some accidents with the robots, so there are security threats. Then there might be additional costs which are not predictable. And you need people who can work and robot, and especially then there's the smaller companies, yeah, they have this concern that yeah, if we buy now a robot and if we change a little bit in the production, then we need somebody to reprogram the robot, yeah, or their own stuff. They get some training, but often this is just some few days. And the company, they make their life then easy. They say, yes, this person we send now to whatever ABB or KUKA, if we buy from them. And then this is now our robot operator and they have to do it. But if you just have some few days of training, then it's not so easy then to program the robot, because you should do this in a very constant way. Otherwise, you have the problem. If you look then, yeah, then you look, yeah, what type of robot? We have seen robots. How is it mounted? Which do we need? And the set stroke, this main direction, how much movements we need there. What is the payload of the robot and with full? Then repeatability is required. Then the accuracy of the positioning or the path. Do we need this different robot to robot? Which speed is required? Cycle time, yeah, obviously what process, and then somehow which tools for the process we need. And there are a lot of vendors for different, for example, weld guns, grippers. There are many of them, and you have to find the right one. Then which control do we need? Some digital input output, or Ethernet, some serial connections, field bus, Profinet. Do we need maybe some additional access? And that's as well possible. Do we need some extra servo controllers? Is it maybe more than one robot? And then do we program them in a master-slave way, or how are they connected to each other? Which sensor we need and which sensor functions? And offline programming, online programming, do we need some extra software for it? And those questions are then what we are faced, and especially then for the smaller companies, there are a lot of questions which they have to solve if they go for a robot. So let's have a look at it now. We have seen already before a little bit. So again, somehow spot welding, arc welding, handling, palletizing, laser cutting, painting, grinding is even possible, and as well assembly. again the repetition of the slide before. So you see there a task which can be done by the robots. So in Germany, it is arc welding. It's nearly and but there's material handling and machine tending, painting, and then other processes assembly. This is how robots are used in the electronic area. For example, for the mobile, this is a big growing area, but not so much in Germany. We look now at welding. This is now spot welding. We see shop floor, and we see that spot welding is a huge area, nearly 1/3 of it. Yeah, so we have the torch, the conduct, the gas nozzle, and the wire. Yeah, the arc welding, and kind of robot handlings. Yeah, but now if your boss is telling you robot, then a deep analysis. Yeah, what is the targeted product to weld? Yeah, obviously you should know which piece to weld. Then what is the product in total? The lot size, time. Then what is with the assembly? Yeah, how are the then the process itself and the work part preparation before. Can you still somehow use the typical workpiece or preparation of it? Those are the which we are faced. Then you should do a feasibility study. Yeah, somehow rethink about the overall product design. Can you change it somehow? Is it somehow different the normal laborers? What is with accuracy and the tolerances of the parts, the size, the weight? Then you should the manufacturing process, the parts of the work part. What is for? Then look at the work process, and somehow the periphery. What is about that? Then which operations are required before the welding? Yeah, and can you somehow make the operation somehow more light? You need more. Those are the big questions. And then the clamping method is important. How you fix the workpiece, that's the clamping. How do you do it, and how quick is it, and is it accurate enough? So those are the big questions. And do you need a vision system, some 2D vision system, some 3D vision system, or maybe no vision system? Then what are the different robots? Do you need some different touching sensors, or do you do it then through the arc sensing? This is possible. Do you need some seam tracking? What is the other equipment what you have in your workshop? Then what is the impact? What it means, does it really make, what is the benefit of it? So you need there as well a rentability study so that you know, does it make sense to use a welding robot or not? So those are questions, with which you, if you go, still you need someone to help build this integrator. Yeah, obviously they should have some, this is so clear. And then not just with robot, but as well with Williams and for the realization. About the cost and the deadline, yeah, pretty clear. Proximity, there is this integrator. Where's the next service if I have a problem? How quick will they come to us and help me? Then what is about some training? How much training do they provide to my people? And is it included or not. And as well, the aftermarket support as the last point. If I want to change something, do they come to my place? Or what is about all those questions and with aftermarket and after sales? Yeah, do they really help me, or they just sell me the stuff and then they say goodbye, enjoy now the robot, and now I try to make more business and just give me a call if you want to buy. Please do not ask me some boring questions about the present robot. So if you have to select an integrator, all those questions are important. Let's have a look to examples now. Sorry, this is the flex speaker. US. Okay, here now, for example, a replacement of a human can do the work as well. The KUKA robot who makes some assembly work, and they say that the robot is much quicker than human. Or with laser cutting, and you see how quick it is. A human cannot do somehow the same in this short. But now, again, if you look for, I've seen that the robot is more precise. What is often somehow one of the main drivers. What is it? Yeah. Obviously, it's the money. Yeah, so this was a song by ABBA, you might know. Yeah, it's often about the money. So let's have a look at the economic analysis. So investment, so we already about it. So you need to buy the robot, yeah, the robot cost, yeah. Then there might be some accessories, yeah, some additional hardware, computer or tools. Then related expenses, yeah, somehow, for example, conveyor belt. Yeah, then safeguarding, this is very important because sometimes there are some accidents. What are the interfaces? Maybe insurance. Then we have engineering cost, feasibility studies, planning, design, installation cost. We have labor and material for the site preparation. Maybe you need pressurized air. What are the setup costs? And then the tooling cost. Yeah, somehow again, labor, material, again, then interfaces. How is it connected to the robot? Yeah, what is with the clampings of fixtures, positioners, tool controllers? This is related to the investment what we have. But somehow, what the operating will be some direct labor savings, yeah, labor and overhead, indirect labor cost as well, maintenance, repair. Yeah. Then the direct maintenance costs, yeah, spare parts, some loops, services, maybe other costs like ongoing training, and other savings, for example, reduced scrap or reduced downtime. Typical life cycle for investment for the robot, that is development phase. So spend the money, and then after a while it should go back, so that you're then at zero, at the break-even point. And after this moment, after the payback, then you should make some money out of it. So the total cost of ownership, it should be assessed, just like the interest rate, lifetime, and initial. Then you have average cost when it runs. Yeah, that's some energy consumption, cost, and the salaries for your operators. Yeah, and in the result, then you have the total cost of ownership for the life. So it could, for example, look first you assume what it is. This is from the template, and then you check it with the real data. This is what you should do, that you're aware, does it make sense and with the robot or not. That you evaluate it when you have installed it. Then you make this table here. If you look now and analyze it, the replace maybe 4 laborers, they earn, let's say, 25K each, yeah, with 2 shifts and 1 robot, which costs 250K. So the source is from ABB, but I've adapted it a little bit for India. So they say that you have a savings of after 7 years of 400 more than 400,000 K. Yeah, this is what they say means in the third year. In the third year, then you make then some money. And but it's a lot, obviously, from the salaries, from the wages, what you have, and how much the job. So obviously you can go there more in depth, but I think in the beginning somehow this is good. So let's come now to a conclusion here. So this Make in India, I think it's a success. Yeah, there are a lot of new startup companies now in India regarding rob. Yeah, and there were different jobs, even high-level jobs, yeah, which had been created, and all the big players in robots, yeah, they have their yeah. Some startups like Gray Orange are now bridging the gap between major players and the MSMEs. Even if they do not compete, but they have already their own unique, which is somehow applicable in different industries. As well, defense, academic research is pulling here a lot. Here the examples, what's Gates attacks, and so on. Now I want to show you with a robot in a different area. Now a robot with mobile. He's a German. He was a world champion, and now he wants a cooker robot. Oh.
Dr. Han, sorry to interrupt, but the video is not playing very smoothly. So you can, if you can,
Okay.
skip the video.
Okay. Pity that I've seen as well that following me that I have some network issues here.
Yes.
As well, usually I explain a little bit more with the slides, but
Yeah.
it does not make too much sense if I'm not very good audible. So I came I'm a little bit quicker than expected. So I think I'm minutes too early. But I did not been that long if the network is not being that good.
No problem, sir.
Yeah. So, but I'm all through. So as I said, I'm a little bit quicker than expected. But if I'm not that well audible, then it means I'm reading themselves the slides, and sorry for that.
That's okay.
Okay.
So can we open the house for question answer round?
Yes, please.
Okay. So the question answer round is open. If any one of you want to ask anything to Dr. Han, you can raise your hand. Okay, Ayush, I have unmuted you. You can ask.
Sir, how we can implement data science and analytic concept on robotics?
The trend they call cloud robots.
Sir, you
And
are
some
not audible. You are not audible to me. What you are saying, I can't understand.
come close to it, maybe now
Still breaking.
better.
Still breaking. It is still breaking.
Maybe now better.
Not.
Let him say something. Dr. Han, you can
Oh,
go on and.
So yeah, you may continue.
okay. So just data in more and more area because which we there is much more even go and more huge research no service, and because they want to have access to all or down to the smallest sensor this day data science production itself. We need data science.
Voice has actually cracked, and I think so student has got this difficulty in understanding. Can we do something like you can just switch the slides and you can just focus on your.
We can request Dr. Han, if student with queries can mail you and you can reply on mail. Dr. Han, will it be fine? It will be fine, no?
Or use there as well my email address.
Yes. Okay. So students, on screen, you can see the contact details of Dr. Han. He is a specialist in robotics. So any query, you can mail him and he will be happy to answer you. Okay. So I think, can we take more questions? I mean, Raksham, taking question from Raksham. Raksham, unmuting you. You can ask.
No, ma'am, not. I'm not asking any question. Just a
Okay.
suggestion. We could ask our question, and sir could literally just type it on the screen, and we would know the answer.
He cannot type on screen. He can
I
show
mean,
the PPT.
like in notes and all, opening word and then typing.
No, that annotation is off. Annotation is off for this meeting. So you can ask question through email to Dr. Han. His mail ID is given. You can ask him anytime. Okay.
Thank you, ma'am.
Okay. Thank you. So Dr. Astha.
Yes, ma'am.
Okay. Over to you. The session
Okay.
is closed now.
Okay. So I would just like to thank Dr. Daniel Han for sharing his expertise in automation and robotics. And we hope it was a positive experience for you as well. So the information you shared was very enlightening, and I hope our participants enjoyed it, even though there were certain glitches being there due to the network. He is being in Germany, and now we can understand the distance problem also. But still, I hope that we can have some future collaborations with you. Looking forward for that. And thank you from our side.
Thank you, Dr. Han. Again, we are collaborating again. First, we met at ElectroCon and again here in SIP. Hope for future collaborations as well. Thank you for the enlightening session. And thank you, dear participants, for your patience. And tomorrow again, we will meet at 10. And tomorrow we'll have a session on analog electronics and digital electronics. So be there on time. Okay. Thanks. Thank you, Dr. Han. Thank you so much.
As you for America, once as well in the
Okay. Thank you.
thank
So
you. Bye.
bye, Dr. Han. Thank you. So I am closing the session now. Participants.
Okay, ma'am.
Okay. Anything you want to share, participants?
Thank you for the session, ma'am.
Okay.
Thank you, Daniel.
Okay. Thank you. And remember, 10 a.m. tomorrow for analog and digital electronic session. I am ending the meeting now. Okay. Thanks and bye.
Bye.